Yeah, so quick show of hands. How many people have ideally the GitHub code space, but otherwise the VS Code option up and running? Okay. And if you walked in since pretty recently, the other thing is if you did start your code space before last night, make sure to run a git pull since we did update those. And otherwise, go ahead and go to this link and start up a GitHub code space, and there's instructions on here. It'll have a few minutes to get up and running before we really get started, so not a huge rush. Yeah. Should we start with the intros? All right, so welcome everyone. I think before we introduce ourselves, one thing that we're curious about was why you all chose to attend this session. And so we're going to do another quick show of hands with the following options. One is who all decided on attending this workshop to see how to interface with databases and other data backends without using SQL. Okay, perfect. Another option is if you're interested in the machine learning or modeling side. Let's go. Okay. The illustration of seeing how it scales up to a very large data set. And lastly, who is attracted by the case study of chess? Who's interested in chess? Okay, couple hands. Guess it makes sense that most people are here for the Python packages. All right. Okay. So I'm Anjali, and a little bit about me. I'm currently at an MRI startup company, and I work on the MRI side, not the AI side, but our company uses AI to try to decrease how long people have to wait to get scans so that they don't have to wait months. Before that, I got my PhD at Stanford and did a postdoc there.
Yeah, and by way of quick introduction, my name is Deepyaman. I've started out working more kind of as a data practitioner, data engineering, machine learning engineering, and slowly migrated towards working more and more on developer tools, including I used to be part of the core Ibis team. Other than that, I work across a lot of kind of open source projects in the broader Python ecosystem. Also be giving a talk on Wednesday around kind of Ibis, broader set of kind of how you can do a lot of this sort of similar SQL-like workflows across the stack later this week. And yeah, happy to be talking about Ibis and IbisML today.
And in contrast, I'm not a contributor in any form to Ibis. And I think that's kind of I think it's a nice contrast because I know what the experience is like as a user and not a user who specializes in these areas. And so personally, I think it's pretty cool and I really enjoyed using it too. So today we're going to be broken up into about 4 sections. We're first going to introduce Ibis and show what it can do. Then we're going to do all of our feature engineering using Ibis. The next part is the IbisML section with the little bit of modeling there. And finally, he's going to show how the Ibis sections scale up to a data set with 6 billion rows. So I think the majority of or more than half the time will definitely be on Ibis, which is a really mature package, and we think that we think that you should go out and use it as soon as you have a chance. A shorter portion is on IbisML, which is newer. It definitely works, but it's not quite as mature, so we just want to be upfront about that. All right. So, okay, I've mentioned Ibis a million times. What is it, and what's the motivation for it? So tools like Pandas assume that we can fit all of our data in RAM on our local machine. But data often lives in data warehouses, so what we end up trying to do is download lots of data onto our machines, load it all into memory, then we experiment with it and develop a proof of concept in Python, since we of course like Python best. And then when we need to productionalize it, we end up having to rewrite all of that code in something more scalable. But data warehouses are typically stored on something bigger and more powerful than this laptop. Plus, the data already lives there. And they have SQL backends that are super optimized and therefore extremely fast. So a much more ideal workflow would be something like taking a small sample of the data and load it using a performant local database such as DuckDB, then develop in Python, but get to leverage the performance of SQL engines under the hood. And then when we go to productionalize it, use the exact same code to process huge amounts of data on the data warehouse where it already lives. And in that way, we get to not rewrite our code at all. And of course, we're at SciPy, so we definitely want to keep all of our code, everything from data engineering to machine learning, in Python. So it turns out that we have a tool for exactly this idealized workflow, and Ibis enables this by providing a single unified data frame interface to more than 20 backends. And if you have any experience with dplyr in R or polars in Python, then the syntax and concepts are pretty similar. And as a bonus, polars is also one of the supported backends. So if you really want to, you can still use polars as well. All right. And with that, we get to some code. So first we have our obligatory import statements. And we'll talk a little about that ibis.options.interactive option shortly. This is the 01 Ibis Basics notebook. Yeah. Thanks a lot. Much appreciated. Do most people have this notebook open? Thanks a lot. Yeah. Okay. So we've provided Parquet files with information on chess games from Lichess. And then later we'll see that there's also a separate Parquet file with information on each move from the different games.
So the question is, why is it in a Parquet file? The data is just stored as kind of a sample of the data, a flat file on disk. Parquet is like an efficient file format for storing this. That's going to maintain also things like your type information. And that's why we've stored as Parquet. The data was originally in like more of a chess notation file, but have already done the pre-processing to get into something that we can kind of work more easily with without having to know a lot about chess.
Yeah. So this is how we read from Parquet using Ibis, but later he'll also show how you can connect to a database instead. And we see that by default, we get a printable representation of the table schema. And so that shows us the name and data type of each column. And for now, everything is a string column, even though we'll see later that some of the data isn't actually strings, or like we'll need to convert it later. And this tells us that there's a 500,000 games from just about 1 day of data. So you can see how this gets pretty big pretty fast. 500,000 games will be about 20 million moves, so that's 20 million rows, and this is just a day. The one other thing you might notice is once we count the number of rows, we're doing this like conversion to PyArrow and as Py. So we'll see in a bit why that is. But for now, we see that like when we look at the type of games, it is in fact an Ibis table now. And .gameID is one of the columns in there. And it is in fact an Ibis string column. But when we go to call the head method in order to peek at the data, you notice that we don't actually see any data yet at all, right? Instead, we get this funny recipe-like thing. So what's happening is that Ibis has a deferred execution model. It builds up our expressions or queries based on what we ask it to do, and then executes those expressions once actually necessary. So it's lazy, or if we don't want to hurt its feelings, we can say that it's efficient. So if we wanted to just see a few rows of the game's table, we could ask for the results of games.head as a Pandas data frame, a PyArrow table, or a Polar's data frame. But that's a lot of conversion for us to do. And that's also the reason why before I was doing the two, when we did the count, we did 2 PyArrow and as Py. But to avoid having to do this, when we're first exploring our data, or first developing our little proof of concept code, Ibis has an interactive mode. And in this mode, Ibis will execute just as much of the query that it needs to in order to show us those like first 5 or 10 rows. And we can refer to this as eager, where eager is the antonym of deferred or lazy. And now, with options.interactive set to true, we see that we don't actually even need to call head yet. We can just have the name of the table, and it shows us a preview. So now we see a bit of the table itself instead of a table schema or a query plan. And a slight side note, unlike Pandas, if that's what you've used most of, databases or Parquet files don't necessarily maintain a particular ordering of the rows. So they don't have that concept of an index. And this is more efficient because you don't need to store everything together. But we'll keep that in mind for later. All right. So we've shown you a table, but not yet what you can actually, if you can actually do anything with the table. So next up are our Ibis verbs. And these are the actions that you can do to a table. And these are going to be select, drop, mutate, filter, order by, aggregate, and group by. So let's dive in. First up, select and drop. Select selects a subset of the columns in the original table. In order to refer to the columns that we want, we can use the string of the column names, like we've done here. Okay, now it actually ran.
I just pulled the code space, but the code seems different from what I'm getting here.
Perfect. All right. Yeah, and an alternative option is that instead of using strings with the column names, we can also use this attribute-like syntax, which refers to the explicitly refers to the column objects. And so here we have our result, and in chess, if you have a 1-0, that means white 1, 0-1 means that black 1, and there'll also be half-halves in the database for draws. And so, in addition to strings or column object references, you can actually mix the two, but I think that might make things a little harder to read. All right. So in this case, if we didn't want to type out games.selected columns every single time, we could use tab completion and get away with it. But Ibis also has a deferred operator, which is the underscore, and you might have noticed that in the import statement before. And that stands for the last table to the left of the current function call. So that's going to be a really useful shorthand later on. So this gives us those same 3 columns without all the extra words. And now we can see that if we do ibis.toSQL, we can see what SQL code it automatically generated in order to do that query. And as a default, Ibis uses a DuckDB backend. And so right now, this is DuckDB SQL, although for something this simple, I'm sure it does not matter. But there's also a dialect keyword parameter to get the same query and any other SQL dialect or any of the supported backends. All right. As far as select goes, or as far as any of the Ibis functions go, there are also these column selectors. And this means instead of manually typing out all of the columns that refer to white, we can do ibis.selectors.contains white, and we get white, which is the username of the white player, their rating, and a few other features that contain white. All right. That's our first verb. On to our second. Drop is similar to select, but we specify which columns to not include. In other words, which columns to drop. So for our first exercise, let's say that the site is pretty redundant with game ID, so we don't need the site column. And we also don't want the column with the day in it, because this data set only spans a couple of days. So how would you show all of the columns except for those 2 days? And you can write your solution up here, and then if you, once you're done, if you want to check your solution and see what we came up with, or if you get stuck, running this cell will load a solution that we provide. So we'll give you a couple minutes. So who's done or stuck, one or the other? Okay. Maybe about 50-50, so give it another minute or two. And does anyone have any questions so far? think we can do right now.
With the drop method, just I'm not too familiar with this library, right? Ibis. So is the drop method like in place or not? Like do you have to explicitly assign that back to another data frame, or is it just?
Yeah, so the question was whether drop, or I'll also answer it for select, is in place or if we have to assign it. And we do have to assign it. So that's why we did this for games selected columns. And later we'll see a different way of working with Ibis.
Maybe to add just a little bit more context also to answer, when you mentioned like in place, that's kind of like more of a pandas concept in the sense that data resides on memory, it's laid out in memory, and in place operations will overwrite data within memory. Ibis is different in that regard. As are like kind of most deferred data frame APIs. So even if you're working with something like polders, which also has this like kind of lazy method that you're kind of building up like what is the set of operations you're going to perform, and then you're going to perform that on the memory. So you're like, for example, here, like when you do like games.select or games.drop or whatever, and you assign it, you're essentially assigning that sort of like representation of that query, not actually data to that object. And so in that sense, yes, you are creating references to that, but there's not really any like, oh, I'm going to override some data in memory.
All right, so I'm going to go ahead and discuss the solution for this. And if we do command enter or control enter, this should run once. Oh, I see. Not that. Okay. All right. So this was games.drop UTC date for the day and site for the website. All right. So far we've seen select and drop, which are kind of subtractive. We get fewer columns than we started with. Our next verb, mutate, shows how we can add more columns instead. So we can create a new column as a function of existing columns. So in chess, ELO ratings are a metric for the strength of a player, and the higher that someone's rating is, the stronger of a player they are. For the sake of an example, we'll say that rating might be more widely understood than ELO. So you want a new column that's labeled white rating and a new column that's labeled black rating instead of white ELO and black ELO. And this is definitely something that we want to be of a data type int and not a string. And if you recall, everything started as string columns. So to illustrate mutate, we take our table, have a call to mutate. We have our new column name, which is white rating, and we set that equal to, you see this represents games.selected columns, so this is our deferred operator, and that's, we take the white ELO column and we cast it to an int. And so when we see the white ratings on the side, we see that they're int 64 instead of string, but that otherwise they match the data, like 2063 for the first player, 2063 here. All right. And of course, now that elo column is redundant, and so we go ahead and use drop again. But maybe we want to do this all together instead of as multiple lines. And for that, we have method chaining. We can build up more complicated queries by chaining one IBIS method after another. So the idea is that the output of many IBIS methods are themselves another table, just like that original games table. So we can continue calling table methods until we're either satisfied with the result, or, of course, if we end up with something that isn't a table, then we're done too. All right, so here we mutate, and do the same thing for black rating that we did for white rating, and go ahead and drop all at once. And we see our black ratings. All right. Back to verbs. Next one is filter. Select selected columns, drop dropped columns, and now filters rows based on some condition. So you'll notice that the others referred to columns, this one to rows. So maybe we're only interested in games where white is a pretty strong player, so white has a high rating. So we can filter for games where the white rating is over 2200. Over the board, that would be a national master. All right. Good, nice high ratings on the white side. And while most of the black ratings are also high, we see that one is below 2200, so we are in fact filtering on white rating. All right. It turns out that this is actually true in nearly 10% of all games. And we can actually combine conditions using an element-wise logical operator. So now this is getting games where both the white rating and the black rating are over 2200. And this happens in 7.5% of games because people tend to be paired with players about their same strength. So if one person's about 2200, often the other person is as well. But that's a side note. So for filter, another way to combine components is that we can list those parts of different conditions as separate arguments. And this also functions as a logical AND. So here we see games where the white rating is once again over 2200, but black won. So over here, we see a game where the black rating was quite a bit lower than the white one, but black won, so this is a nice upset. All right. Yes?
When you're counting these, the percentages, what's the two pandas for? Like you have countants dot two pandas.
Is that just to get a number? Yeah, just to convert it to a regular number. Yeah. Oh, sorry. The question was why when I'm calculating these percentages, there's a call to two pandas, and that's in order to get a regular number.
Yeah, so specifically, this is coming from two tables. One is coming from strong games, and one is coming from game selected columns. Since they don't share the same base table, right? These are essentially unrelated expressions in a way. And so we're just kind of looking at metrics from each of these constructed tables. But if you wanted to look at this as kind of a single expression within IBIS, you'd need to write it in a way that it's kind of off of that same base table.
Is this basically transformed into a different overall data type when you use Ibis?
So the question was, is this being transformed into a different like data type when you are using Ibis? Ibis is a data frame API. So you can think of it as kind of like an authoring layer for your logic. So you can write your logic in R, or you can write your logic using a data frame like Ibis, or if like probably everybody here, I'm guessing it's used Pandas, right? But you also have things, you can consider Pandas as like an execution engine, because Pandas has logic for how it executes like this logic using whatever NumPy or Arrow or whatever kind of way it's done depending on the version under the hood. But Pandas is also kind of like an API. So for example, you have like BigFrames, which is the Pandas API running on BigQuery, or you have Snowpark Pandas API, which is basically that Pandas API. So you write stuff that looks like Pandas code, and it runs on Snowflake or PySpark Pandas API on Spark. So similarly, you can think of like Ibis as like an API layer. So this is a way that you can define your transformations. And now, no matter how you're defining these transformations, that gets compiled to some sort of representation under the hood that gets executed wherever you're actually running it. So here, by default, it's running on DuckDB, and like Anjali had showed, it's you can compile that to DuckDB SQL, and that like whenever you're like if it's in interactive mode, or whenever you're doing like two pandas, it's going to submit that query to DuckDB, and it'll get back the results, and it'll get back like if it's getting like a head, it'll get like a limited set of results. And similarly, that same code, you could take it and you could have it targeted against something like ClickHouse or Trino or whatever. And then the last part is like kind of what is that actual stuff then we're operating on? Maybe this is kind of getting into like more of that, like how does it work from an implementation perspective? But DuckDB is Ibis is essentially operating on like information, like that metadata about the table, so your schema. So very early on, before it went into that interactive mode, you would have seen like where it said database table, and then I think it was like, oh, showing all of these are string columns, and here are the names of the columns. So when you know that your data looks like that, if you know it has these columns, and these are the types of the columns, that gives you enough information to figure out what are the different sorts of operations you can do upon it. And based on that, we're basically doing all these operations. And then whenever we actually want the results back, then we are making that submission and getting results back. In interactive mode, which is not like the most performant mode, but it's the way like you can kind of like see results most quickly, that is happening on every time you're you have like kind of a result going out to the terminal.
It's here's the type. I hadn't actually rerun it, so it's still down here. So the question was, what is the type of strong games or any of these .count calls before we convert it to .pandas in order to get a number out? Did I answer the question, or?
Yes. I guess I'm still maybe confused why. I guess you can't do operations on scalars.
Because they're not related.
Yeah, so basically the question is like, why can't you do an operation combining these two? So if you look at like kind of, I don't remember right now off the top of my head. I might need to go up like what is so strong games is kind of like game select columns, and then it's filtered down this way. And well, actually we can just do it real quick. So if I was to do this, I think that it will not work. Actually, I can just take this out too. Oops. Oh, shoot. I just switched the table. Okay. Let me check. Yeah. So it involves. So this is kind of what I was saying. That it has multiple base table references. So essentially, like whenever you're doing like a relationship or like you're doing a computation, in this case, because strong games is like a filtered version of game selected columns, that is like a separate table. And here, like game selected columns is like that root table. And so it's like, so if you were to like think about this, I don't know, are you familiar with, or have you written like SQL code? So you can think of that you need to be able to select from game selected columns. But here you're doing like select from game selected columns and strong games at the same time, no join logic or anything between them. Or it's like kind of like selecting, or similar, like even if you think about like pandas, right? Or if you were to like select two different columns, but they're like one is from a different version of the column, where it could have been that you filtered it down to like 20 rows, and you can't really kind of like select across these columns unless you're explicitly joining them somehow. So that's basically the same reason. Whoever.
I think she was first.
Go ahead.
Do you have any advice on making a decision about when a data set is too large for pandas and using
So the question was, when is a data set too large for pandas? On the Pandas website, I remember many years ago, there used to be like some rough guidance around like kind of how big of a data set you can use with pandas. I think some people will potentially disagree here. But in general, if you kind of look at the benchmarks, I think it's pretty clear that at most scales, pandas is not the like most efficient option anymore. Pandas recently has made strides in terms of performance. So especially with kind of like taking on the Arrow backend. But even then, like pandas is generally slower than some of the more kind of modern alternatives like polars, or if you're using something like DuckDB, and you can use DuckDB with your pandas, with your Python API here, using something like Ibis. So I think the first thing is like if you're working with like small data, like under a gigabyte or something, pandas will be perfectly fine, but it's almost never going to be the most efficient. Most cases, polars or DuckDB will be more efficient locally. The other workflow, and like this is one of the ones which you really want to avoid, is if your data lives somewhere else already. So if your data already lives in a database, you almost never want to bring your data in locally, then process it, and then kind of push it back up like to a database. That's rather inefficient when most of these databases are kind of like efficient compute machines of their own. Hopefully that helps. Yeah, you had a question.
Yes. For what is my understanding, but maybe I am wrong. So basically, Ibis, what it does in, let's say, back of the curtain is it handles the query at the end, and it never touches effectively data until when you call to pandas, interactive, whatever.
Mm-hmm.
Like what you do, also from the type that spoiled me a little bit, you always act on the expression itself of the query, never on data.
Yeah, whenever you're building up that expression, so the question was like you're generally operating on the kind of like schema information and like kind of building that query as opposed to like actually modifying the data. That's correct. Ibis is just going to be kind of essentially building up like a query plan of sorts that you can do this. There is, so I mean, I can potentially try. I can't remember if I have this dependency installed here, but I think, let me see. I'm trying to remember what the syntax for visualizing the IR is. Maybe I can actually go and pull up an example here.
Maybe a couple other random tidbits in the meantime. So we mentioned how it works on different, lots of different backends. It uses SQL glot under the hood in order to get those different dialects. And then also there was a little bit of discussion about like pandas and size and like DuckDB and things like this. One of the nice things about DuckDB is even though it is local, we can basically use a, we're basically limited by the like hard drive size and not by RAM, whereas in Pandas, all of your data does need to fit in RAM.
Mm-hmm. Yeah, so I don't have the GraphViz stuff installed in this tutorial right now, but here's just kind of an example of like another place where it kind of done some transformation using Ibis. Here's a resulting, like we'd seen something like this database table. And you can see that there's been some transformations done here, including like some joins and filtering. And then we call this visualize on there. This requires GraphViz to be installed. And you can see that Ibis essentially constructs this representation of given our like tables, what are we going to like in this case, there's like an orders table and a payments table, and we're making a whole bunch of selections and like aggregations and various like modifications of tables. We're joining them together, combining them, and this is actually like what we call like an intermediate representation that Ibis builds up, and then it submits under the hood for you. So this is why like Ibis is like an API layer, building up a query plan, and then you choose like this execution backend that's going to actually accept this query plan. If you're familiar with how things like Spark work, or this is actually like in Polders also has like essentially like intermediate representation, and it builds like a query plan. This is how you have this kind of like also lazy execution model. These all kind of have this sort of similar shared model. And then Ibis's like unique factor is that it is not an execution engine. It is entirely an API layer that allows you to choose whatever is the execution of engine of your choice based on what is the right situation and like wherever your data lives and so on. Happy to also talk about this more and go into like some more depth later if you're kind of curious about that more. Maybe we can do that. You had one question, or all good?
I was going to say, just kind of super quick add-on, right? Because I recently read the Panda book by Wes, right?
Mm-hmm.
It's the real Panda. So what Wes actually recommends, because Panda would actually try to write to memory, so if you data size, usually, you know, if you data size, you know, like the memory size on your computer should be at least like 5 times bigger than data size. Because there'd be other overheads running at the same time. If it's bigger than that, you either run the car or run a DB storage with it's for optimization.
Yeah. So just to kind of real quickly repeat what he said is that based on what Wes McKinney, one of the creators of Pandas, had written before, like you should probably have at least like, I think you said 5 times as much memory for what you're working with for Pandas. Maybe to add on to that, like just as a kind of counterpoint example sort of thing, there's like a example of a benchmark using Ibis with DuckDB. We're operating on about 1 terabyte of data, and the person doing that had a very beefy machine. It was 96 gigabytes of RAM, but still, basically, like you should pretty comfortably be able to work with like 10x your RAM size of volumes of data with something like Ibis. And then when we're talking about, and that's for something where with like DuckDB. And then we're talking about like your distributed engines. I mean, that can just scale however much your like clusters and things like that are set up for. We'll see an example of that kind of in that last section where I'll demonstrate working on like a much larger data set that could have even been larger. If you are also curious about this, you mentioned Wes, who is the creator of Pandas. He's also one of the creators of Ibis initially. So Ibis has been around for, it was created, I think, over a decade ago initially, and then kind of like picked up more recently. If you're also curious on reading more about this, I think he had written an article a while back around like 10 things I hate about Pandas, and like more on the, not on the Pandas hate side, but more on this like kind of lessons, the power of some of these other technologies like Apache Arrow in this kind of more modern composable data ecosystem. I'll leave it at that and let you get back to where we were.
More verbs. So, as you can probably guess, these are all very naturally named. So, order by orders the rows in our table by the specified column. So, it sorts. And Ibis enforces a default of an ascending order across all of its backends, even though some of those backends will have a native default of descending. So it's kind of nice because you'll get the same thing out regardless of what backend you choose. So when we sort by white rating, we see now that we get the minimum white rating. And probably we're more interested in who are the strongest players. So in order to get it in descending, we can use this syntax. And now you'll notice that you'll see that all of the white titles are GM. That stands for Grandmaster. So not too surprisingly, the strongest players are Grandmasters. All right. So for the next exercise, how would you show the 10 games with the highest white rating where white nevertheless lost? So just as a reminder, 0-1 means that black won, so white lost. All right. And if you do end up finishing early, go ahead and start on exercise 3 as well. just to get a sense, who's done? Okay, and I should have specified who's done with exercise 2. 3, so. Okay, give it one more minute and then. No rush, but for folks who have started on exercise 3, are there any questions or places where you're stuck?
I'm trying to figure out the syntax.
So there's a question about syntax, I'll just come on. All right. So I'm going to go ahead and show a couple solutions. For this first one, we first filter to get just the games where white lost. And then we order by a descending white rating to get the strongest players. And you see that there's still some grandmasters, and they tended to lose to pretty strong black players too. The next exercise was kind of a bonus one, and so this one was to see if we can show the 10 biggest upsets. And for this, the way that I wrote this was that I first created a new column using .mutate called winner margin, where I used cases, and in cases where black won, I subtracted the white rating from the black rating, and in cases where white won, did it the other way, and then ordered by descending margin, so the most negative is the biggest upset. And so here we see black is much, much stronger than white, but the result was that white won.
What does cases mean in this circumstance?
So it's kind of like a switch statement or a case statement in other places. It's basically a lot of like if-elses, but all together. Yeah. And in Ibis, actually, before this version, the function was case instead of cases, and it was like looked a little bit different. That's changed recently. Yeah. Yes.
Can you change multiple conditions of the cases within a single tuple, or is that
Can you change multiple conditions? It might be a little hard.
So
to
so the
describe.
question was whether you can have like multiple conditions, as in like instead of having like a 0, 1 here or a 1, 0 here as kind of like the string that you're checking equal to, if you can have like kind of more like a Boolean condition. Yeah, so you can do that alternatively. So I think there were some examples here in the documentation, probably, or maybe not. Okay, so this example here is where, as is with the example there, where you're checking for a certain value. But if I go here to getting started for SQL users and go to, I think there's a case. So let's see. Cases. Yeah, here's an example of ibis.cases where you are passing in like an expression, and here you can also create like more complicated expressions. So here, as an example, it will be. Let me make it a little bit bigger. Yeah, here. So ibis.cases, if the column like the TWO column is negative, then it will use like this can be an expression resulting in a Boolean column. This can be just any other expression that you will use as the value for the resulting column. Here again, like it would be the 3 column. Otherwise, if it's not meeting either of those conditions, it would use the else condition. So and then this condition, as long as it's resulting like in a Boolean expression, it could be like a complex thing you can do with like ands, ors. You can build up an expression.
All right. And in that example, we like really see the value of that deferred underscore operator, because we're able to refer to a table object which we didn't assign a name to. In other words, that winner margin that we use over here, it isn't a column in games selected columns, so we wouldn't be able to order by it unless we had that deferred operator. We couldn't just use like tab completion to save typing, and we would actually have to like split that into 2 statements instead of getting to do it all chained together in one. And now, when we look at that like built-up SQL that compiled SQL, we think, I think that even for doing a not that complicated operation, it's starting to look pretty hairy, and I personally find the Ibis or the Python more readable than this. If you did come up with a different solution, it's possible that that generated sequel is going to look slightly different, but in practice, any small differences in SQL won't make a difference. And the reason for that is that any modern SQL execution engine will optimize the execution of queries. And so if they contain variations of the same sets of operations, it's going to end up with no measurable performance difference. Okay, next up is aggregate. And there's several functions that we have to summarize data: mean, max, min, count, sum, kind of your standards. And we can call a method for example here, mean, on a column, and get an Ibis scalar. And then there's also an aggregate function, which, and we can also use just ag. And like, aggregates really make more sense when we pair them with a group by. So group by creates groupings of rows that have the same value for one or more columns. It doesn't do a lot on its own. We really should pair it with an aggregate function to get a result. So here we see how many of the games involved titled players on the white side. So we see some grandmasters, some women's international masters, etc. And we see that Ibis will generate an automatic column name when we do this. And if we just use ag without something like mean or something like that, that's just going to tell us what the distinct values, or if we have multiple columns, what the pairs or sets of values of those grouped columns are. So here I'm just using a couple of the categorical columns that are in there. And so this is just for the sake of an example, but we see all the different combinations. In order to not just get different combinations that exist, we can actually pass an aggregate function, for example, a mean, to ag. And so here, we once again group by the title, for example, Grandmaster, International Master, etc. Then we take the mean of the white ratings for players with that white title. And then we can, once again, chain methods. So this is just a standard way of working with Ibis and some of these other deferred things, is to chain methods together and do that after that ag call. And what this gives us is we get a sense of what are the highest titles. So for example, Grandmaster is at the top with the highest mean rating, International Master, FIDE Master, etc. All right. And one other thing is maybe you don't like the automatic name that Ibis gave, so we don't have to stick with the default aggregate data column name. We can also choose our own. Here we call it average white rating, and this does exactly the same, but we see our favorite column name instead. So in the interest of time, I'm gonna go ahead with these. And so the next one was so the next exercise was what the different results, how many white wins, black wins, and draws were there in games involving at least one grandmaster. And if you're interested, you can try that one out after this. or actually, I'm going to go ahead and run it. And then we're going to compare that to games where both players were untitled. And so here we see maybe about 5% of games ended in draws with untitled players versus about 10% of draws between grandmasters. So the higher the playing level, the more games happen to end in ties or draws. All right. And finally, we're going to use group by and ag, which is what we're going to affectionately call aggregate, to get a better understanding of what the time control column contains. And time control tells us how much time each player gets for the game. So that in chess, if a player runs out of time, they lose the game, regardless of the position on the board, basically. All right. So when we look at that time control column, we see that there's a number plus another number. What that is the first part is a base time, which is the number of seconds each player starts the game with. So for example, in this first game, each player has 180 seconds or 3 minutes on the clock, plus an increment, which is the number of seconds that's added to each player's clock right after they make their move. And so if we look at this fifth game, each player starts with 2 minutes on the clock, and for each move they make, they get 1 second added back. So an average game is about 40 moves long. So in order to get a sense of the effective total time each player gets, we might want to see the base time plus 40 times the increment, and then convert it to minutes, because I just think minutes are easier to understand. But before we do that, we want to first split this time control string into the base time and increment. So we find our plus sign, which is our separator, and then we can use substring in order to split those, and then cast to an int, so that we don't just have strings anymore. So I think it's pretty nice to be able to do this without iterating through all the rows. And in the event column, Lichess, which is where we got this data from, categorizes games into different ranges of time control. So classical games are the slowest, then rapid, then blitz. Bullet games are very fast, and ultra bullet games are ultra fast. And correspondence games are basically untimed. And so we see that the event column includes these in there. So we can figure out the minimum and maximum amount of effective time per player for each of these game types. And in doing so, we can confirm that our understanding of those different time control types is consistent with the data. So we're grouping by event after throwing out some other things. Then we're aggregating using a min and a max function. And then we're ordering by the maximum effective time to get that ascending order again. And so, yes, ultra bullet, bullet, blitz, rapid, classical, correspondence in the order that we predicted, and the maximum effective time of one category is slightly less than the minimum of the next. All right. There's some more bonus code at the bottom if you're interested later. But this is the end of the first section. So we're going to take a 7-minute break. So that should be till 2:55.
So I just thought also, I'll point something out while we're here, and we just saw this example. One of the questions earlier was around like, why can't we do that division of the counts, right? Which was coming from like a couple of rooted columns. So we'll see a lot more examples of this later, but this is actually like a good example of when you can do combinations of different columns. So here, for example, we calculate that split index, and you see split index being reused within this expression as like where we're doing that substring on. Basically that column, so a per each value for like what is the index where we find the plus. Similarly, like the base time and increment are computed here, and then we do base time plus 40 times increment. So in these cases, we are able to combine these columns because these columns are all rooted at the game selected columns table. And that's why it's essentially like a way we're able to kind of build up like kind of more complex logic around here, kind of in a like decomposing it into like several Python statements for readability and reuse. So just thought I'll point that out since we were just seeing it. So yeah, this is I just thought to get it from like a article which I've written before. So here you can see, for example, that. So this is. I guess most likely you haven't used like DBT before. Have you ever used DBT like for SQL transformations? Just curious. Yeah. A data building tool. It's fine if you haven't. This example comes from that, so I just thought in case you. But
I'm super ignorant.
No. That's I wouldn't expect you. I just thought just in case. So this is like an example with like payments and order data. And this is a breakdown of essentially how IBIS represents it.
Yes, but exactly like my question before was triggered by the fact that when you type when you type an IBIS expression, it gives you the type of the expression that sounds like we can look about IBIS expression dot
Relations or table or something.
exactly,
Yeah.
sounding like an IBIS expression that will return a table or that will return a scalar or that will return so on and so forth. A little bit like a query does, that at the end returns either a table or whatever. And so my question was, if IBIS is really just building a query on the background, and every time that then you go interactive, it applies the query. But if you don't go interactive, it just builds the query, and he's super happy. I mean, he's building his own query, and then when you will apply and go interactive, the query will be applied to the data set.
So specifically interactive is like an IBIS mode where you are submitting the query,
Constantly.
you're compiling and submitting it constantly, right? And otherwise you have to just do it explicitly.
Exactly.
If you use polars, for example, and you're familiar with like the lazy frames, you have to explicitly do a collect.
Yeah.
Similarly, like there's IBIS like as an execute, and if you do also like 2PyArrow or 2Pandas or 2polar or something, that's also doing essentially an execute of sorts under the hood.
Yes, exactly.
Yeah.
So my question now comes, does the performances advantages that IBIS provides, that I trust, I've never used it, but I assume so, mainly come from the fact that you handle not in an interactive mode, so let's say in a more real world situation. Does it come from the fact that you really submit the query just once at the end, or also from other design?
So IBIS does a little bit, like a very little bit of like kind of optimization of your query.
Okay.
So an example that comes to mind is if you're like selecting, or let's say you're dropping some columns, but then it's way more efficient to select the remaining set of columns and do like a little rewriting like that. But on the whole, like IBIS, it does not really have performance benefits per se because it is only an API layer. The benefits come from whether you are using DuckDB or Polars or Snowflake or Oracle or whatever you're using as your execution engine. And IBIS will essentially give you the same performance characteristics of that engine. So the biggest reason why IBIS, in a way, like whatever we're doing right now, is going to be more performant than doing it with Pandas, is because it's using DuckDB under the hood by default. Or even if we had chosen Polars backend or something, it would be more performant. It's not because IBIS is doing anything special, it's because of that. But the thing is also that DuckDB is a SQL database. You may not want to write SQL, or you may like some properties of Python that the fact that things are more testable, or I can chain things together more cleanly, or various other things, or rest of your code bases in Python. And in that sense, IBIS is giving you that like Python API. The last thing which we'll cover a little bit at the end is that you can take that same code and you can run it on like a different backend if you need to scale. So I'll give an example. You can run stuff on like Trino in the cloud, or people I know, they use pollers for their local development, and then they do Spark, they run production Spark with the same code. So like that's another benefit. I've also kind of given like how you can use the same logic and run it in like it will be DuckDB or something in batch, and then you can run it using this link and stream like if you need that. So that's just another benefit.
Sorry to interrupt. I was going to say that it's like past.
Yeah.
So sorry. Thanks. So I see most people have come back. Thanks. I just want to really quickly mention there were some questions about the syntax on cases. We saw that the pre-build has Ibis version 9.5, and that's before the change from case to cases. So apologies for that, but you've seen the new syntax now. And with that, I'm going to hand it off to him.
All right. Well, welcome back. So now we've kind of gone through some of the Ibis basics. Now that we've done that, we're going to look at things kind of more specifically towards our use case. We kind of very briefly mentioned this, but what we're going to be looking to do is to build like a live win probability model for a chess game. I know most people are maybe not so familiar with chess, but you can think of this, I mean, if you're familiar with something like soccer too, right? You may think that like kind of at various points through the game, based on a variety of different things, could be the like kind of score, or in the chess game, it could be like the valuation of the position, could be like based on like certain characteristics of like how the game is going, could be in our examples, like because somebody has like less time, there could be a lot of varieties which kind of make it so that we don't just think like, oh, it's 50-50 chance of winning. It could be just basic things like one player is much better than the other, right? Like if we take like a grandmaster and somebody who learned to play yesterday, and like from the beginning we can kind of guess like, oh, what is the live win probability? It will give a lot more benefit to the grandmaster to start with. So in short, yeah, we're just going to do this as an example of building a live win probability model. And what we're going to do for that first is feature engineering, essentially like what are going to be the inputs to our machine learning model that we'll build in the next section. And in order to do that, we'll also take a quick look at a little bit more data exploration on top of what we already did, especially looking at like some of our moves data. So this is going to be the 02 feature engineering notebook. I'll go ahead and run that same imports at the top of the notebook. I'll talk a little bit more about why we're creating this list of game level features. We'll have this game level features list. We'll also do similar stuff for like move level features broken down different ways. And then let's go ahead and reload our data snapshot. Everything's in interactive mode here, just so we can see the results. So first we're going to start with our event-based features. Events has some useful information for us. One of the things we notice, even just looking at this snapshot at the beginning, is that we see that all of these things in the event column are starting with the word rated. We can verify real quickly whether that's actually true for all of them. So here, very similar to your pandas sort of function, we can look at the value counts. We're going to do everything with a string manipulation, removing the length of rated. So, or taking that first part of the length of rated and see how many of them are rated, how many of them are something else. So here we see that for 16,000, the vast majority of them are rated. The rest of them have have a variety of different prefixes. So what we see here is nothing says casual, nothing says unrated. There's no like opposite designation of rated, but instead, if it's rated, then it'll basically say rated, and then what we talked about as being our time control, whether it's blitz or ultra bullet or something. And if it's not rated, it'll just go ahead and just start off right there with ultra bullet, which is ultra B here, because we've just done the first 6 characters, bullet, blitz, rapid, classical, so on. So based on this, we can create our first feature. So our first feature we're going to create is rated. And that's pretty simple, whether it starts with the prefix rated, we put a space on there just to be a bit more precise. And that is going to give us a column. With that is rated column, we can also just do things like our value counts on it, so we can see like our distribution of the feature. So we see, as we saw earlier with the kind of breakdown by that first 6 characters and had other categories there. This Boolean is rated column is going to have, is the vast majority true. 416, 417,000 true, 7,000-ish false. We are going to add this feature to the list of features that we have. This is going to have like a useful property for when we're going to combine all of the features together. We've talked a little bit around how these are kind of reusable expressions. So that has to do with it. Also for that, we're going to go ahead and just give it a name so that you see that we get like a reasonable sounding name. It's very descriptive, starts with event, or sorry, starts with like a function call, and that it's an event starts with rated, but is rated would be kind of like a more reasonable name for us in that final table that we have. So we'll give it a name before we add it to the list of features. Okay, what else can we do? So let's look at what are the kind of the popular event values here. So as we discussed a little bit, we see the time control there, blitz and so on. But then we also see whether it's like rated blitz game or rated rapid game. But then we also see things like rated ultra bullet tournament or rated blitz tournament. So that means that we can get some additional information out of this. So the first thing would be, what is that time control type? We talked a little bit about that before, how whether it's like a super fast game, slow game, somewhere in between. So similar to like some of those examples before, we were looking at like time control and reusing some of those intermediate values that we create, like base, time, or increment. Here we're going to reuse that is rated feature that we have created earlier. This is especially useful if you've ever done feature engineering yourself for machine learning. You don't want to have to rewrite your logic each time for like kind of common like intermediate computations that you're using, or computations that you both want in your like to be there like kind of as a raw feature for your machine learning model to be able to potentially use, as well as like that's going to be an input to other features. So here, the fact that these are also expressions means that we can reuse them. So here we're going to use that as like a condition. So if it's rated, then we can then we'll go ahead and like take it only the part after that rated prefix of the event. Otherwise, we'll go ahead and just leave that whole we'll leave that whole event information there, and we can look at the different types. So we after we remove that rated part, then we just went till the next space here with that find space. Just because we've done a little bit of data exploration, this looks pretty reasonable. And we can go ahead and add time control type to our list of features. One of the things to note here is when we're creating this list of features, we need to make sure each of those names is only added once if you do happen to add something multiple times. So right now, if I was to go ahead and look at game level features, this is gonna not be like the prettiest looking thing, but we see here like we have Leech has time control type and is rated. I think we just have 2 of them so far. But if we did end up like accidentally adding another column named is rated to this, it'll create a problem when you go to combine your features. Just because we can't have duplicate column names, just keep that in mind and be careful when you're adding to that list. All right. So I'll just give a couple minutes here. We're going to create another feature similar to that is rated for whether it's a tournament. I know that in the previous notebook, we did a little bit more complicated logic, like, oh, is it have tournament or does it say Swiss in there? In this case, let's just do it super simply. Whether it contains the word tournament in there, just take a second, add it to, and just compute this is tournament value. If you need help on the docs, this link for contains, it should take you to the relevant API, but it should be quite straightforward. Okay, so probably for this, we can just go ahead and do something like contains, and we can look at some of the values here. So these are like lowercase tournaments, so we'll just check for lowercase tournament like so. Oops, sorry, games dot. We need the right column, which is event contains tournament. There we go. And if we look at that we see most of these at the beginning are false. So probably it's more useful to look at something like we could do mean or value counts. Let's do value counts. And we see, most of them, like 376,000, 377,000-ish of them are not tournament games, but a good number, almost 50,000 of them are. So we have a good mix of games in here. If you didn't get that, or if you got something that you aren't so sure about, you can go ahead and also load the solution. And if you are to just run this cell, you'll see the similar thing. And last but not least, let's not forget to add this to our list of features. Okay, so next thing is going to be our ELO-based features. So as Anjali mentioned, ELO is kind of like a comparative measure of skill. It's something used in chess. It's used in a lot of other systems. So like if you've never played like on online games with like matchmaking, a lot of these have like an internal ELO system as well. For these, they were originally string columns. We can just go ahead and convert them to integers, and we can go ahead and add it to our list. Similarly, we can do that for black ELO as well. And these are going to be useful. We just convert them to int because, they're comparative measures that are continuous rather than being kind of discrete categorical variables. Next, a little bit more complicated. This is the exact same logic that we saw in the previous notebook, so I'll go through real quickly. We can find our time control information by first finding where is that plus sign, and then converting each of the components of the time control to an integer. And we can go ahead and add our base time and increment to our list of game level features. Didn't mean to hit enter there. Okay, I just went through those quickly because we've already seen some of that logic. So last but not least, for game level features, since we're looking to do some predictive machine learning work here, we want to define our target variable. In this case, we can define our target variable pretty simply. So we're just going to predict a continuous 0 to 1 value at any time for like our live win probability. The closer it is to 1, the more likely it means that white is to win. And then the closer it is to 0, that means the more likely it is black to win. When it's closer to half, that means it's either like closer to draw or closer to being something that we're just not sure about that outcome. So here we can do that using a case statement. Actually, yeah, I can see I forgot to update this, but I think as Anjali pointed out, cases is the new standardized syntax. Case still worked here, but it is deprecated. So here I used a case. This would have worked if you're also using like an older Ibis 9 point something version. So yeah, here we've gone ahead. Whenever white won the game in the end, we're going to give that as a target value variable of 1. Whenever black won in the end, a target variable of 0. If it was a draw, of 0.5. All right. And we'll add that also to our list of game level features. We'll just call that target column. So we mentioned earlier that by adding all of these to a list, we can kind of exploit like an interesting property of the fact that these are not just columns that we can like see the values for, but also the fact that they are expressions. So because they are expressions, here this star basically means, if you haven't seen this that much in Python, it basically means that we're going to splat out an iterable. So we're expanding out the contents of a list as a set of arguments that are added to this function. So we are able to just select game ID in addition to all of these game level features, because they're also expressions. We don't need to join them or anything. They're just computed based on that games based column. And so we see this is like a preview of what our game level features looks like. So we see our game ID is rated. The other features we calculated, like the time control type is tournament, elo's time, and finally our target variable. Okay. The next thing we're going to look at is move level features. So we're going to spend a bit more time on this because we haven't talked about it before. When I've ingested this data from the raw format, so in the raw format, this is basically a bunch of games in chess notation, have parsed it using something called like a Python chess library. And I've done this ahead of time, one, because I don't want to spend so much time in the intricacies of parsing chess games not really related to Ibis. And then second, because it's something that's not that efficient, especially if we're doing across like a large set of data. When I've done this, have kind of done it, have split it into like a somewhat normalized form, by which I mean we have our games table, which is what we've been looking at so far, that has like an identifier for the game ID, as well as like a lot of things which are game level information. So like in the span of a certain game, the players don't change, or their elos are not going to change, or it's not going to be like, oh, it was a tournament and then it wasn't, right? That's just the general information about the game. In addition, we have like information on a move level basis. Because if we want to look at the live win probability, we want to do more than just make a prediction at the beginning. We want to be able to make a prediction at any point during the game as the situation during the game changes. So here's kind of like what that games table looks like. You can see that we have our game ID, and then we have this column called ply. Ply basically means if you're familiar at all with chess, I mean, you've got a white and black player. When white makes his first move, that's going to be our first ply or half move. When black makes the first move, in return, that will be our second ply. That way we can distinguish what is a first move for white and black. So it's essentially like a half move. And then we also see some additional information in this comment field that we've extracted. For the sake of simplicity, we haven't extracted any information around like, oh, what are the pieces moving and what's the state of the board or anything like that. If we want to take this like really seriously and beyond like a tutorial scope, we could do all of these things. But for now, we've just gotten some of this information, which I think is quite useful as a comment field. So specifically, the games that we've filtered here have this comment field, and it includes move-by-move computer evaluations, which we can use as a proxy for how the game is going. So for example, if the evaluation says like 2.00, that means that white has an advantage, because it's positive, of about 2 pawns worth. I'd say don't worry too much about like the specifics of chess evaluations here, but we're going to basically say if it's positive, that means white is better. If it's negative, black is better. And the bigger the number, the more white or black is winning. The closer it is to 0, that's basically like, oh, more like a dead even position. The other type of evaluation that we're going to see here is one starting with like a pound sign. So that indicates that we are in like close to a checkmate with optimal play. So we take this example that we mentioned here, like pound -4. Again, negative means black is winning. So here that means black can force white to get checkmated, or basically that's the lose end of the game within 4 moves. Maximum, even no matter like if this is black plays the best possible options to him, if white plays the best possible options available to him, black can still force a win. So this is evaluated separately than like that kind of numeric scale, which is like a material advantage, just because this goes beyond anything. This means like a win is imminent as long as you don't mess it up. This is a little bit complicated. Both in terms of, well, explaining it, but also in terms of how we're going to parse it. The chess library that I mentioned handily has a regular expression that we can just kind of reuse for parsing this information out of that comment field, because so the games come in a standardized portable game notation format, and so there are libraries that enable us to do the parsing of this and not have to figure everything out ourselves. So we will go ahead and create something, a list again for evaluation-based features, and then we are going to import that evaluation regex, and we're going to go ahead and extract that. You can see here that we are using an escape hatch for Ibis. If certain things cannot be expressed within like kind of Ibis's syntax directly, Ibis offers kind of like a variety of escape hatches. One of them is the ability to drop into SQL for the dedicated backend. So in this case, we're writing things in SQL that will which will get compiled and executed then on DuckDB, just because we don't have like a great way of expressing this using Ibis syntax. This is also useful if you need a certain function, which maybe is not available within Ibis. We won't get too much into it. Ibis also has other ways to drop into kind of backend native functionality. This is a question that, like, as maybe you come up, or if you've used other frameworks similar to this that come up, is that, how do I make sure that Ibis supports 20 backends, that I'm not just limited to the lowest common denominator of that and not able to actually accomplish like kind of more interesting functionality. So this is just an example of an escape hatch through which Ibis allows you to make sure that you're never limited by the syntax of Ibis. Okay, so we can see here that using that fancy regex that we just went ahead and imported, we are getting our prefix, mate. This is our regular evaluation, depth and suffix. We're going to ignore prefix, suffix, and depth and really focus on mate and regular evaluation. You can see that we explicitly listed out the set of fields that we were extracting using this regexp extract function that came from this eval regex in the library. That's useful. I'm just pointing this out because you'll have to do something similar when we look to parse the clock information. Let's look at a separate game, and we'll look at kind of like the end of that game also to see what does it look like to have a mate evaluation. So here you can see towards the end of the game, this means white is imminently mating. I mean, this 10 moves out. It's still pretty hard for a lot of people to see, but probably is winning by quite a bit by this point. We can also see that this is ply 79. So that means essentially both players have made about 40 moves each. And then you can see that since they've been playing pretty reasonably, it looks like that the mate continues to go down. So we're getting closer and closer to mate. I don't know exactly with this game. I'd have to look it up, but most likely either black gave up or black ran out of time or something like that. Okay. We can also see, and this is going to be useful for how we want to kind of like normalize the score, what is the longest mate that we have in the database. So we can use one of our aggregation functions just to see what is the absolute value, so black or white mate the maximum one, and apparently there's something in this set of games where there was a mate in 121. This is not really realistic, but computers can see out very far, and this might have been something which is kind of like stored. We can use this as like a bound for like, okay, we at least want to make sure to handle up until then, but we can use an arbitrary value like 1,000 as our mate score. So essentially, we are going to compute like a score that is going to increase instead of decrease as it gets like closer to winning. So for example, if it's a mate in 1, because we set our mate score arbitrarily at 1,000, we'll do 1,000 minus 1, so 999. Or if black is about to mate in 1, it'll be negative 999. This will allow us to distinguish it more from a score like +2 or -5. Like -5 is a pretty big advantage for black, but it's nothing compared to minus 999 when black's like, oh, I'm going to just mate him the next move. So just with some simple arithmetic and using a sine function, we can look at this mate evaluation score. And we can add these to our mate evaluation score as well as a regular evaluation score to our list of features. And in this case, we have not just our game ID, but also game ID and ply as our combined key columns to like identify each unique row. But we can look at all of our features here so far. Again, if we look at that game, where we like a specific game where we also see a mate score, here we can see what became like a mate in 10, mate in 9, mate in 8, converted to 990, 991, 992, as compared to like our very early on evaluations at the start of the game. Evaluation is like very barely in favor of white, 0.17, so it's a big difference from there. Okay. So now we'll let you all take like 5 minutes to do something similar with the clock-based features. Clock-based features are actually like one of the reasons why I started to look into this out of personal interest was, so I play a fair bit of chess. I have also, since I was a child, been terrible at managing my time, both in chess and pretty much every aspect of life, and constantly run super low. And I'm like, how many of these games am I losing and playing just terribly just because I have like, a few seconds left? How much is my like kind of win probability going down because I'm going low on time? I mean, that's pretty reasonable to think, right? Like even if I give you an extra, I don't know, let's say you play a lot of chess and you have like an extra queen, that should be winning by a lot. But if I tell you, now you have 1 second left to win the game, you're probably not going to win unless you're getting back a lot of time on each move or something like that. You're much more likely to make a mistake. So that's why, clock is another interesting piece of information, and it's available in that comment. So let's initialize our list for clock-based features, and we can use the clock regex to parse it out. So this will be pretty similar to that eval regex. All right, I am going to go ahead and continue here. Hopefully people had a chance to get through some of this exercise. It should look very similar to what we did for the eval. So here we're going to do similarly the regexp extract with the clock regex. You would have had to look up in that linked documentation what the clock regex looks like, and we know that it has hours, minutes, seconds, as well as that like kind of prefix fields that we're going to pull out. If we run that, we can see, for example, on this first ply of this game, 0 hours, 10 minutes, 0 seconds. So essentially that means we are starting the game with 10 minutes here. So we can take like another minute, if you haven't already, to look at how can we make this into something more meaningful, like from a computation perspective. This will be more just a regular Ibis code. How can we get from our hours plus minutes plus seconds columns just into a seconds columns, like a total seconds for the clock. So yeah, I'll give people just like a minute to do that. Oh. So if you look at this, so the question I'll just answer for everybody is, where are we getting DuckDB from? Ibis has a bunch of different backends. Here's a requirements.in file. It's like a requirements.txt file, which I compiled into, but just for reproducibility, I defined my requirements loosely and then compiled it into this automatically. But you can think of this as your requirements.txt file. And you can see here that for my imports, I have Ibis framework with the DuckDB and Trino extras. So if you want to use Ibis with a certain backend, you just specify the, like as an extra, the backend name, and that'll include the dependencies for it. And that's how we've been able to use DuckDB. We skipped over all the installation and everything like that to make it easier, and because we provided a development container, a dev container, which has everything already set up for you. But if you are going to go use Ibis yourself, you will essentially need to install Ibis with the appropriate, like whichever backend for whichever engines you want to use. And so there'll be like 20-ish options for this. And before we get back to the other part, like one other thing which I'll just kind of mention more broadly, because there have been some questions on like, oh, databases and how does Ibis working with some of these SQL and things like that. So Ibis, so this is from like a blog article that I'd written earlier this year called "Does Ibis Understand SQL?" But in short, like even if we are writing something like this, which is like t.sql and then select x as u, so we're selecting the column x and we're renaming it as u, where x is greater than 0, but we're basically writing this as a SQL statement. Even though we are writing this in SQL, instead of using like Ibis expressions per se for writing this, this is being parsed and understood by SQL, by Ibis. And you can essentially apply this to different SQL backends. So it's being represented in this case as like so this is like our in-memory, like intermediate representation. Like how does Ibis view your query plan? And here we have like a SQL string view as part of our representation. And so that means that if you were to go and you were to attach it to some other backend, that should work as long as that's compilable. This is this article, like also if you're just curious, like what does it mean? Like how do we get to this, like we show like, oh, to SQL if we want to generate like equivalent SQL, and what is Ibis actually executing? Like it goes through this whole explanation of like what does it really look like? What's actually it being represented as under the hood? This is like well beyond the scope of this tutorial, which is more focused on the user aspect. But since there have been some questions on it, if you are curious, yeah, this is just an article there on the Ibis blog. So you're welcome to check it out or ask me later. All right, I will go back here and continue. So this will just be a simple arithmetic operation. We use a try cast here just in case there are any null values or like invalid values there. And we will see that, yeah, so this was what we started with, like 10 minutes instead of looking 600 seconds. Okay. So if you, let me close this. All right, so we can see this better. So if you've been like thinking about this still, we essentially have the time left after each player's move in that clock column. But that means that in that first column, for that first row in a game, that's going to be the time left after white makes their move. And then for the next row, it'll be the time left after black makes their move. And the next one will be again after white made their second move, essentially. So if we want to look at something like how much time did they spend on a move or something like that, it's actually going to be one move apart. Like there'll be like, it's essentially like an alternating thing. So in order to do this, we can use window functions, and the concept which is there in whatever data frame library, Pandas, bowlers, or also in SQL, in order to compute what is the previous clock value. This will be what we can actually compare with in order to see like how much time it was for that on that player's clock. So on the second, so basically we want to be able to be like on that first ply, how much time did white have on the clock and how much time did black have on the clock? So we can go ahead and lag that column. So this will basically be like shifting the clock column by 1 in order to get the previous clock column. And then we can, so here we have like 60 seconds, and here we can see that we've shifted it down by 1 with the lag. And now with this, what it basically means is white's clock will be the clock value if it's the odd ply. So like, since the first move is made by white, and the third ply is made by white, so then on all of these odd numbers, we will see that the clock column represents white time. On the other ones, it represents the previous clock then is black's time. And it's flipped. On even ply, clock is going to be black's time, and previous clock is going to be white's time. Based on this, we can go ahead and select out white clock and black clock as two separate columns. So yeah, these are long auto-regenerated column names. We can see also that we're missing black clock on the first one, but we can just fill this with the white clock value because both players should have started, unless it's some weird situation, with the same time. And we can use another common function there called coalesce. We can go ahead and add these features to our list of now clock-based features. And now if we select these, all from the moves with the parsed clock, then we can go ahead and see, for example, for this game, both players start with 60 seconds. This is the one that we filled in, white clock, black clock, and we can see the time going down as the game progresses. So last but not least, we've got all of our different features that we've computed. We want to combine them all. We want to create our model input table, including all these features, the key columns, and our target variable. We can join just based on these key columns. So we'll join based on the game ID and the ply for all of the move level features. And then we'll join that with the on game ID with our game level features, and construct our model input table. Right, so here we see our game ID. Later, much further over on the table, we'll also see our ply as our other key column, but we'll see all those features we constructed initially: is rated, time control, the elos, the initial times, as well as our target variable. And then with our ply, we'll see our evaluation-based features as well as our clock-based features. So these are going to basically be all of our features that we're going to use for machine learning model that we're going to build in the next section. Last but not least, if we were to look at the end of a game, the mate evaluation, if it is mate on the board, if it's one move away from mate, it's like mate in 1, but there's no such thing as mate in 0, so we're missing an evaluation there. For these, since we know the final result of the game, we can just fill it in with, if the final result was that white won, then we'll just go ahead and give it that maximum score. In our case, it'll be our mate score, so 1,000. If we know black won, we'll fill it in with negative 1,000, and if it's draw, we'll give it a 0 score at that point, just to make sure that we don't have incomplete data. So we can just go ahead and fill that in. We'll also remove some of the games before we get into the ML part of things that we don't really care about or might and might not be kind of useful or interesting to look at. These are going to be games where we don't have any time information, and also I think it's generally not that interesting for like a casual unrated game to be trying to predict the whether, like, what that live win probability is going to be. This can get thrown off because for some of these like websites where you play, like, oh, you can, there's not really any regulations around like, oh, are you cheating, or is somebody playing on your account, because these like games don't matter. So that's why we're going to just filter it down to only rated games and not any of these untimed games. And we will write this out. We'll write this out to a file. You can also take a look at that final SQL. This looks very unreasonable, but if you've actually done or like kind of looked at like a lot of SQL-based data engineering work, a lot of times, like especially in the past, you would see massive SQL scripts that teams would basically be maintaining that are containing like a lot of the metrics that people are computing, and they look like this. Things have gotten a little bit better as some of the SQL tooling has evolved and added some more software engineering practices, but this is not really all that unreasonable. So yeah, in this last bit, we can go ahead and just write this out to a Parquet file. I think that we also have actually provided like a small model input table just so we can kind of move faster on the next notebook. So with that, I will hand it over back to Anjali.
Okay, so IbisML is a library for building machine learning pipelines, and we can create recipes to pre-process our data before training our model. After we have our recipe, which defines a series of last mile pre-processing steps, we can chain a recipe together with scikit-learn estimators into a pipeline. So in this fashion, it seamlessly integrates with sklearn, XGBoost, and PyTorch through Scorch. So we're going to go ahead and import everything we need. And we could pick back up where we left off by loading that Parquet file you just wrote out. But we definitely recommend that you go with this small model input table instead. That other one with 500,000 games, times 40 moves on average, times 2 would have about 40 million rows. Maybe not best for the code space. All right, so we have all of those nice features that we just engineered. So first off, we're going to split our data set into our training and testing set. The majority of the rows will go into the training set, with those chosen pseudo-randomly as per usual. And that's the data that we're going to use to fit the model. And then we're going to use the testing set to measure model performance later. But one of the first things that I'd mentioned was how Ibis and other data based things don't maintain a particular ordering of rows typically. So we need a key in order to be able to split the data reproducibly. And so to ensure that the moves corresponding to a particular game aren't split across the training and testing sets, we're going to only split by game ID instead of splitting by both game ID and ply. Basically, we're trying to avoid data leakage. All right. Okay, so what this ends up doing is puts 75% of the games into the training data, and the rest into test. And now we define our xtrain as all of the training data with the exclusion of the target, which was our actual result, because that would be cheating to have in our features. And then our ytrain is just the target, but we're multiplying by 2 in order to convert the 0 for black win, 0.5 for draw, and 1 for white win into 0, 1, 2, so that we have class labels for a classifier. And we do that same thing with the test. All right. So in order to, we're going to define a preprocessing recipe and then use that to fit and transform our X-train and then later our X-test. So our recipes are series of last-mile preprocessing steps. So that can be things like converting qualitative features to one-hot encoded dummy variables, transforming groups of features. So for example, taking a log transform or adding polynomial terms, filling in or imputing missing values. And if you've used scikit-learn before, they do a lot of the same things as scikit-learn's data transformers, but they instead use any Ibis-supported backend. So basically, those backends might be efficient for this kind of like very basic math, but as we might touch on later, like maybe those SQL backends aren't later going to be the best for modeling. So this allows you to put the preprocessing parts into, push those to the backend as well. So we'll see. All right. So now we're going to define our first very simple recipe. And so here we're going to drop any columns with 0 variance. So they're all the same across in all the rows of that column. And we want to drop, and we want to look at all of the columns when determining which ones have 0 variance. So this is a column selector, and that column selector is IbisML's like dot everything. And then we're going to drop all of the string columns. So in this case, the column selector is dot string. So that selects all the string columns. Okay? All right. So when we run fit, that processes our recipe using our training set. So in this case, any features with 0 variance in the training set will be slated for removal. And then transform applies that recipe to the training data, which creates the final set of process features that the model will use during training. Dot to Ibis transforms a fitted X-train and then converts it to an Ibis table. So that's why you don't see an explicit dot transform here. And then later on, we're also going to apply the recipe to X-test. But when we do that, that's going to be without redetermining anything in the recipe, because that would also be cheating. Okay, so this dropped is the is-rated column, because we only had games which were is-rated is true. And any string columns. All right. So now it's your turn to add to this recipe. All of our features need to be encoded as numeric data types. And for some inference methods, float works best. So how would you cast all of the columns to float 64 at the end of this recipe? So we'll give you a couple of minutes for that.
Yeah, so if you do need, and it probably is useful to know, if you go to ibis-project.github.io/ibis-ml, that's where you have the documentation for IbisML, and you can find the documentation including for the various steps and things that are there.
How are people doing? Okay, so we're just going to cast everything to float 64. Otherwise, maybe for cast, we might want to use like ml.numeric, but we've already dropped all of our string columns in this case. And next, we're going to fit a model with a pipeline. Let's run. All right. Thanks. Yeah, next we're going to fit a model with a pipeline. So as I mentioned, we can chain a recipe, specifically the one that we just wrote, with our choice of scikit-learn models. And in this case, we're going to use an XGBoost classifier. And we're going to specify a number of estimators in hopes of avoiding overfitting. And then we're going to fit our pipeline using xtrain and ytrain. After that's ready, we're going to get a sense of our fitted XGBoost model by plotting feature importance. So with importance type of gain, that tells us kind of how much we improve the purity of the classes by each of the on each of the splits which use that particular feature. And then importance type of cover is a different metric, and that tells us the average number of samples that were impacted by splits using a feature. And so that just gives us, as mentioned, a sense of how important those features were. All right. So we see that our evaluation of the position and how close we are to a mate are most useful in seeing who's likely to win a game at that point. And same for cover. And now we also see that how much time is left on the clock is also pretty important. So I think this is kind of as we would expect. This is an XGBoost model. Gain and cover are the two metrics.
It's I think it's a permutation feature.
Oh, sorry. Thanks. Yeah, so the question was how the importance is plotted or determined, yeah. What method, yeah. And then we score our models. And then since the test score is pretty similar to the training score, it's going to be a hand-wavy suggestion that we didn't overfit the training data too much. Right. Next, we're going to use what we trained in order to predict. And so we're going to predict the probabilities of each outcome on the test data set. And then we're going to define our win probability as the probability of white winning plus half the probability of drawing. And for binary classification, we, of course, normally use log loss. But in this case, we also have draws. So we have 0.5s in the target. And so if we think about a 0.5, even if we correctly predict a white win probability of 50%, we'd get a log loss of 0.3 approximately. So, of course, log loss probably isn't the most theoretically sound thing to use here, but for the sake of simplicity, we're just going to run with it. And so to make it slightly better, I'm just going to adjust it by subtracting off the loss corresponding to perfect prediction. Please don't tell any mathematicians or statisticians. So that's what these extra functions here do. All right. And so let's take a look at our losses. Okay. So the loss that we get is less than if we just predicted the mean of Y train for every single row. But it's a lot worse than perfect prediction. So one concept of like maybe what's going on here is that we're making guesses for after every single ply. And so a lot of those guesses are like near the beginning of the game when we have very little information on how it's going to go, right? We expect our guesses to get better later on. And so here, I'm going to just kind of messily print them and see, like, yes, at the start of the game, we might as well have just predicted the mean result. But by much later in the game, our log loss has gotten quite a bit closer to perfect prediction. And the loss of the perfect prediction increases with move because more of those games end in draws. So you get a sense of what percent are draws from that. But anyway, all right. So this is how I've just plotted that. And we see the improvement as the games go on. Okay. So XGBoost, I think as many of, tends to have very good performance, and you don't have to think too hard when it's like tabular data. You just kind of throw it in. But the downside is that it's not that interpretable. And so we're also going to create an interpretable model with logistic regression. Interpretability aside, from the point of view of an IbisML tutorial, the advantage of logistic regression is we can't just throw things in and have to do more feature pre-processing. So we get to illustrate those. And so these initial steps are the same as we did before, but we have additional logistic regression steps that fill in missing values with the mean of those columns on the training data, or from the training data. And then they normalize the variables so that you can get coefficients even if all of your data was at even if your different columns are at different scales before. And you can see how I've added a few steps from two different recipes together to make one recipe before. It doesn't work to just there's no direct way to put recipes together, or at least not at the time that I did it, but this is the way I figured out, using just tuples. All right, and so we once again have our pipeline. We have a new recipe with a couple extra steps, and then instead of an XGBoost classifier, we have a logistic regression, and we once again are going to fit that using our X train and Y train. And keep fitting it. Okay. All right. And when we score, we see that we do get a fewer percent of the rows correct than we did with XGBoost, but once again, the training and test score for each model is about the same. So that's not too bad for that first model that you learn about, really, but yeah. All right. And if we had just predicted a white win, which is the most common outcome for every single row, we would have gotten a 48 percent right, so that 62 is better than that, so that's another thing. All right. That was also predicting the probabilities as before and taking a look at them, and we can compare between XGBoost, which is the blue line, and logistic regression, which is the green. So they follow similar trends, but XGBoost, of course, outperforms logistic regression, especially as the games go on and there's more that the features could be used for. And the advantage is that we also get interpretability, and we can take a look at the coefficients that we get. When I looked at these, most of the coefficients made sense. There's a positive relationship, for example, between how much time white has left and that white's likelihood of winning, and the opposite for black. The one exception was these rating columns, where the higher that white is rated, the less likely they are to win. So that could come from a couple different things. One is that once we account for the effects of all of the other features, rating might have a counterintuitive effect. Right? So to check that, we can fit a model using just those two features, white and black rating, white and black ELO. And then the other advantage is because they're on the same scale, I don't have to standardize, and so then I can apply the coefficients directly and see what happens. Yeah. So here, I drop anything that does not end with ELO. And so this is another of those column selectors. It's just like not of ends with. Yeah, so this also is all IbisML things here. All right. So we get our coefficients, and now we see that they kind of go in the right direction. And then I saw, like, okay, how big of a difference it makes? Well, it turns out if white is much higher rated than black, then white is predicted to have a much higher chance of winning. But this is actually less than you would expect, like, based on definitions of ELO ratings. And there's, like, a theoretical percent that they should win based on how many points apart ratings are. That's how the ELO system works. So there might be a few things going on. One is, like, there's a lot of fast games online. And so maybe people are, there just has a lot more variability. Also, a lot of the games involve players with ratings that are very close to each other. So maybe ratings isn't a very useful predictor here. And then it turns out that maybe what I think is definitely the biggest factor here is that it turns out that Lee chess has, like, some weird tournament games that don't follow the rules of normal chess that we didn't quite account for. And I think all of this goes to say with that, like, none of these packages save you from doing your, like, exploratory data analysis and actually looking at your data and seeing if things make sense or not. Yes?
So here you use logistic regression with, I think, just like the standard parameters. Can you, like, use Ibis with like cross-validation up to 200 parameters?
I think that's, like, one of the things that's challenging is that a lot of those types of steps make more sense in Python than on a backend. And so I think that's one of the things that we'll, like, discuss.
Yeah, I mean, just to expand on that a little bit, like as mentioned, like this is one of the places where IbisML, especially at training time. So the idea with IbisML is that you are doing this on an Ibis backend, so it could be some sort of database backend or something, and then you have your modeling happening, but your modeling is not going to happen on a database backend. And so this means that you will have some amount of data transfer being required from that like database context to whatever, like, especially if we're thinking about like at scale, like your model trainer context. This is, so in working on IbisML, like the long story short is I kind of look at like, okay, especially if you're looking at like kind of very large scale, how do people be it like maybe in like Pinterest or in like FlightAware or somewhere else where they're actually dealing with like petabytes of data and they're training on petabytes of data. How do you do this? A very common approach would be, rather than doing more of this on your database engine, potentially to be doing more of this on your trainer infrastructure. And in that case, yeah, you have like more of everything is in one place and you can do everything in there, rather than like kind of having to do more on like a separate backend where you could access with Ibis. On the flip side, like there were also some people kind of who were mentioning like, okay, if you are working with a kind of very large scale, you might be simplifying your like kind of, you might not actually do as much kind of like cross-validation, or in like later stages as much cross-validation and like kind of that iterative process in practice. And that might be kind of more during that experimentation part. And then when you want to scale, then you are just going to like do that once without like not as much like hyperparameter tuning at that point or cross-validation. So I think this is like, kind of as mentioned, like one of the areas which is still being figured out. I'll talk about this maybe a little bit more later. IbisML is pretty new, a year-ish old. There are also some other kind of packages that are in this space. I don't think that there is any like kind of established, like this is the best way to do things in a way that also scales. There are also kind of like some gaps in the ecosystem that are like being considered and worked on that might help enable like some more of this, especially as you need to get to scale.
I saw a feature selection in IbisML's documentation. It has one function that just drops your variance. It's not actually like more sophisticated feature selection.
Yeah. Yeah. And I think another part is like, if you do use IbisML for the pre-processing, or like if you do use IbisML, possibly one of the places where you do see advantages later is at inference time, where the pre-processing is going to work well with Ibis, and then the like inference portion can be done with like user-defined functions. And maybe a different way to think about scaling is like, I think in a lot of cases, subsampling your data set is enough for training. It's in other places where you really need that scale, for example, at inference and other things. So I think, but yeah, definitely like a discussion of like very worth having. Yeah. All right. Okay, so this like model with just ELO like definitely like doesn't do great, but yeah.
Training is less than taste score.
Luck.
The training is 49%.
I think there's random chance, and I don't think there's anything else.
They're very close, right?
Yeah.
So, and like if anything, the training score being close to the test score is just that it's not like overfitting anyway.
Yeah.
It could have been the other way around, but like they're so close, it doesn't really matter.
Yeah.
What is the chance level, right? 50%.
The chance is not quite 50% because there are also draws in the data set. So the question initially was why the training score is very slightly less than test score in this case. And I think that's just random luck. They're just close because we haven't really overfit. But like, yes, we would do very similarly on the test set by just having predicted white win for every single thing. Like, all of this goes to show that, like, by not handling those, like, very strange games, rating isn't a good predictor on this data set. Like, this is not an illustration of, like, a like a good model. Like, it's definitely, yeah. And if anyone is interested, if you later filter your games to exclude anything with tournament in it, that should improve things a lot. So, yeah.
Sorry, maybe a comment on this. I would expect in a situation like this model, rating not to be a good parameter to evaluate the black or white to win, because as you said before, you always couple players with very similar rating. But on the other hand, I would expect rating to be a good parameter to divide different trainings and observe how, for example, time is differently important in different ELOs. Or, for example, how a position in a very high ranked match is very good for one side, while for low elo is not the same, because maybe they are weaker and they cannot see very complicated moves or stuff like that.
Yeah, so this is, comment was that perhaps we would expect rating to not be a good predictor on its own, but that if we look at games where both players are of different, in different like classes of ratings, really high or really low, that the model may look different. And I completely agree with that. I think that's right on, yeah. So what I'm trying to do is really quickly drop the tournament games and show what happens. So okay, taking probably too long to do this. Okay, yeah, so you see that in this logistic regression model now, suddenly higher white ELO leads to a higher percent of white wins, and higher black ELO leads to a higher percentage of black wins. So it does have that effect. Yeah. And now when we look at like a very strong white player with a very much lower black player, we see that a win percent that's predicted by a logistic regression with just the two ratings is now 95%. So this does change things. Now we'll fix that very quickly. Oops. Did I miss something? Oh, it just hasn't run yet. Okay. That's okay. So after that slight digression, we're back to XGBoost. And maybe we can improve our model a little bit by creating a few more features. So for example, the difference between how much time the players have might be useful. Like it might be telling, for example, if white has only 5% of their time left, while black still has 95% of their time left. And we can do this type of last mile feature processing using IbisML. So we have this ml.mutate, which does the same thing as the IbisMutate verb that we saw before. And so we've defined a new feature, a new column called relative clock difference, which is a function of white clock, black clock, normalized by that effective time formula that we'd seen before. And when we fit and transform, we see that added on as a new feature. Okay. So, unlike logistic regression, a garden variety XGBoost model doesn't directly incorporate linear relationships between the features. And so maybe we think that the difference between the two players' ratings is more useful than the individual ratings. So you can take a couple minutes to add this feature onto this recipe. How many people have got something down or think they're ready? Okay. All right. So this might be something like ml.mutate, rating diff equals, once again have that deferred operator. White, yellow minus dot black, yellow. Yeah. Okay. So as before, we chain everything together. We once again use the XGBoost classifier with 20 estimators. Train. Plot our features, importances. We see our ELO diff somewhere on one of the plots. Okay. Score model. And we see that we do very, very slightly better on both the training and the test sets than we did with our original model. When we plot things, we see that it seems to like only make a little bit of a difference at the beginning of the game when we like don't have any meaningful position-based evals to go off of. So not too much visible improvement, but we said that we were going to make a simple model, not an accurate model for this tutorial. So I'm going to say that we stuck to what we promised. All right. And next, we might be interested in seeing, well, like, what do these win probabilities look like for some games? Like, we've been talking about clocks and things. Do they actually make a difference? And as you can see, for this, I've just converted everything to Pandas. And so obviously, if things were at a large scale, you would definitely not want to do this. All right, so first off, we see a game where black is much stronger, but it's also like a very quick game. Okay, so with black being much stronger at the beginning of the game, we already, the model already assumes that like white doesn't have a great chance of winning, and that gradually approaches 0 as black's position, so as the evaluation gets worse and worse. And then the red dots are when there's a mate available. Okay. And then in our next example game, we see like 2 reasonable players, and the life win probability doesn't change too much until this point, and that's when white makes a like huge blunder, and suddenly black is like winning. So this is like more than a rook down. at this point. So that's as we'd expect. And in our next example, we see this point where the evaluation is a plus 7.5. So that's more than a rook up for white, approaching a queen up. But the model thinks that white has like about a 10% chance of winning. So the question is, what is happening here? Like, did the model just really mess up? And then when we scroll down, we see that white has 10 seconds or maybe 5 seconds left at that point. So basically, this tells you that, like, and this is a game where there's no increment. So white doesn't get any time back on their clock. Like, when they run out of time, they're just, like as they get low on time, they're just going to run out of time. And so the model correctly realizes that. So that's that. Since we talked about scaling and we teased this a little before, I'm now going to hand it back to Deepyaman for
All right. So we've been talking all this time about how we're building machine learning pipelines that can scale, but we've been doing everything essentially locally. And we've been working with a sizable amount of data, but nothing huge, something where, yeah, pandas will be a little bit slow maybe, but DuckDB polders would have also handled this probably without any issue, right? But what if we're working with a particularly large amount of data? So actually the reason why I started working with this Lichess data set is because Lichess, it's an open source chess server. It's probably the second most commonly played on server. And one of the really nice things is that they publish all of their games out as archives. And I didn't necessarily need to do something about chess, but I needed to kind of show how you can work with terabytes of data, and where am I going to find terabytes of data freely accessible while working on open source software. So this looked like a great fit. And so we're going to look at a full month worth of data here. So I'm going to go ahead and import Ibis again. We're going to, instead of using DuckDB as the backend, we're going to use Trino, which is another computing engine, and we're going to use a managed platform called Starburst Galaxy, which allows us to kind of spin up a large Trino cluster. As you can see, we can connect to Ibis very much the same way, but here we're going to specify our backend.connect. Here we could have also done ibis.duckdb.connect, but here ibis.connect is going to by default go to DuckDB with a kind of in-memory database. Here we need to specify that we're using Trino, and we also need to pass in some of our authentication information. So I've populated a .env file for that includes my whatever password, what's the cluster name, so on. All the information that I need to connect to Trino here. And this is going to take a second. This is just to test our connection, that we can do connection list of tables here. We should see games and moves. It's going to probably take a minute and a half just because the cluster needs to warm up for cost reasons. Don't keep it running. In the meantime, though, let me hop over to our data. So our data in this case, we're still using Parquet files, same Parquet files actually. But this is for a full month hosted in S3. This is split into our games data. So we can see here we have, I think, 5 files. Yep. And it's just over 4 gigabytes of games data. This is super compressed Parquet data. If you exploit it out, it ends up being kind of orders of magnitude larger, especially when we get to the moves data, just because there's a lot of repeated information that gets compressed. And yeah, if we go back here to moves, we'll see I think it's about 20-ish gigabytes of compressed data here. So this is a month worth of data. We'll see a little bit more on the information for that. We've connected our catalog here, our Lichess catalog, that is pointing through our Amazon S3 data using, and then we've got our cluster that we've spun up here. You can see here was when I was using it, but we've got basically a 20 node cluster that we're going to be using for processing this. Okay, let me also just go over to, this was, we can also take a quick look. I think this added just a little bit right now, but basically this was the total cost spent just in the past couple days on running this on this kind of larger data set. So also, this is running off kind of like a trial and with some free credits from Starburst Galaxy to avoid spending hundreds of dollars. Okay, so we saw it took like 90 seconds just because it takes about 1.5 minutes for the cluster to start up. We can test out our cluster, our connection further by just doing like a quick select statement. This is not going to get back any large amount of data because we're going to limit it to 10 rows. Yep. Sorry?
You might want to zoom back in. I think
Oh, sorry. Okay. Let me zoom in so it's bigger. Okay. All right. Hopefully that's more visible now. So our data looks kind of like what we were working with before. I think there's some kind of extra processing that was done on the snippets that we had provided. We'll do that additional processing in a bit. I don't think that some of these columns, I can't remember if some of the columns like eco and things were all there. So how many games do we have, and how many total ply do we have? So we've got about 87 million rows in the games column, so it's 87 million games. And for moves, I think it's about 6 billion-ish rows that we're working with. So this is definitely not going to run with kind of pandas locally, or even polars DuckDB are going to most likely struggle with this unless you have a very large amount of RAM. I think I actually I did process some of this locally, or on a local cluster using DuckDB, but that was with 1 terabyte of RAM. Otherwise, it's not really workable. Okay, so we're going to basically take our same kind of an initial filtering logic. So this was something that we'd already done ahead of time. We'd filtered it down to just the games containing evaluations. So we're going to do that, see how many games we have with evaluations. That's about 700, 800,000-ish. And we can join that with, sorry?
8 million.
Sorry, I can't, about 8 million games. We can join that with our games and moves columns to get down to our filtered set, which looks more like the data that we were working with. Most of this code is just going to be basically directly copy-pasted from what we had before. So we got our is rated, our game level features. We're going to just copy-paste all that logic in here. Of course, we could have abstracted that into some functions, but since we're doing it across notebooks, we basically copy-paste this. So what we had mentioned is that Ibis is kind of a good way to unify kind of your logic across how you would run things across different backends. That said, Ibis is not magical. There are certain areas where Ibis cannot necessarily kind of abstract over all of the differences, and it does its best to say okay, if you write your logic a certain way, that we will guarantee your results look the same as much as we can. Ibis is a massive test suite that runs on every single commit. for like basically testing with various data scenarios on all of these backends to make sure that like all these functions as close as possible give you the same results. Because hey, if you're going to move from DuckDB to Trino or to Snowflake or whatever, you don't want like there to be like some, oh, we've introduced some interesting new artifact because of how this database backend processes things. That's one of the things that Ibis will try to take care of for you. But like things like regexes, every database has its own sort of way of handling regexes. So you can see here that our regexp extract stuff is slightly different just because the dialect supported by Trino is a bit different than that supported by DuckDB. Other than that, all of the logic is pretty much the same. So, okay, we've gone ahead and processed that. Let's do our same stuff with getting the mate evaluation. We'll create our clock-based features. Again, the regexp extract is slightly different in terms of the syntax. And we can construct our model input table here. Okay, and we also wanted to make that, so one of the things, if you remember back on the feature engineering notebook, is we added that like final evaluation. If it is a mate, then we give it based on the result of the game. Yep, and we take out our unrated games and our correspondence game. And we can look at the head of our table here. So I think this probably takes like 30-ish seconds to, yeah, 20 seconds to run. But this looks like what our model input table was like. I'm just going to kick off the next one. I'm just going to see like how many rows are in our model input table in the filter set. But this is the set of columns that we had before as well. So I've already also gotten our IbisML recipe from before. I had just, so that same recipe that we built, I just pickled it, and so I'm just going to load that recipe up. So with this, like, we are not going to train it again, right? Like, we already trained our recipe on that smaller data set, but we're going to load that, and with the kind of like whatever parameters and stuff are stored there, we can apply that from an inference perspective. And we can take this model input table and execute it, and we should see the results of our preprocessing shortly. Oh, sorry, we already saw our results of preprocessing here, my bad. And this is the number of rows. We see that's the same number of rows. But we can see like some of these like diff columns and so on that we created, as well as like the filtering of non-numeric columns and conversion to float 64. The last part, which I'm not going to run, and this kind of comes back to it comes back to the kind of what we were discussing earlier around being able to transfer the data across. So at this point, like one of the limitations is always going to be that your you can do as much processing as possible on like something like Starburst Galaxy, but then most of your kind of like modeling packages don't actually run on all of these kind of distributed backends, and they're not going to just be like simply like, oh, I can drop in Ibis and I can start doing like XGBoost inference on Trino or something like that. You need like a specialized sort of thing for that, or you need a way to transfer the data. Right now, by default, it will just, if I'm to use something like scikit-learn and like score it, it's going to try to convert that all, because scikit-learn is very pandas based, it'll try to convert that all to pandas, and that is just not going to finish running, or it'll crash the kernel, one or the other. We can, just for completeness sake, I think if I refresh this, we should probably see, yeah, we saw like, okay, some more usage was done, probably built like whatever 15-ish dollars. You could also look at it in terms of like some of the other usage, but essentially we were able to kind of process data at a scale which we weren't otherwise able to do it by using Trino without really changing much of our logic. And I think that this is also a good like segue a little bit into like the state of like some of these different things that we've talked about today. What is kind of like, as Anjali had kind of alluded to earlier, like kind of what is in a state that's like very mature, like, oh, okay, this is something that we should be using. What's a little bit more experimental? What are some of the other like kind of packages and advancements sort of happening in this space that maybe, since we have a few minutes, we can talk about. So the first part, we went over Ibis, and we used Ibis for both initially some data exploration, as well as like your more like data engineering-ish sort of like feature processing. Ibis is essentially going to be doing like your SQL equivalent sort of workflows and putting this like Python familiar data frame API on top. And it's very good at that. Ibis has been around for a while, and it's kind of gotten to this point where it's quite mature. It's gaining in terms of, I'd say, people knowing more about it, talking more about it across the data ecosystem, and that's still kind of catching up. It's definitely not as like well known or talked about as much as something like Polders, or even like or DuckDB or something. Those are like definitely more recognizable names, but you see Ibis being used more and more across these places, and I'd say that it's quite good for this, and there's really no reason not to kind of like check it out, especially if you're looking for some of these benefits. One could be, hey, I just want to use Python and be able to interact with these database backends. Second is, I want to be able to ease the transition from either dev to prod. So like if I want to like experiment locally with something that's good locally, Polders, DuckDB, something like that, and I want to be able to then scale that without having to do a lot of rewriting code, right? Like if you think about like what was the job of a machine learning engineer, especially like a few years ago, a lot of it was basically like, oh, I take Pandas code and I productionize it, which means rewrite it in something that scales. A lot of the idea is you don't necessarily need to do that if you think ahead. And then the last thing is like even in terms of unifying between other paradigms like streaming and batch. So one of the things which we didn't touch at all on here is Ibis also supports some streaming backends. So for example, if you, the way actually I got into using Ibis was kind of working on a real-time feature platform for machine learning workflows. And so if you're like, let's say you're working like fraud detection, most companies that are working on things like that, yeah, they're computing real-time features. But then for like backfills and like historical experimentation and things like that, they also maintain at scale these like Spark pipelines or something that's good for batch. And they maintain two sets of logic. And by using something Ibis, not only can you unify between like dev and prod, but even between things like streaming and batch. So that's like kind of another use case for this. So then we get into like the ML aspects. This is definitely a lot more experimental. I'd say that I think IbisML has been like officially released kind of for use like probably about a year or so. And it's one of those technologies which is kind of looking at improving the way that you can scale some of these machine learning workflows. To add like what are some of the other things? Like, well, one is scikit-learn is very embedded right now, and it's usually sufficient, right? Otherwise, like you do have kind of these dedicated approaches, especially for like certain algorithms that you can take advantage of, kind of like larger training clusters, GPU training clusters, so on. But for a lot of these kind of, especially tabular data science workflows, I mean, scikit-learn is very widely used, and for a good reason. It's also very widely supported. One of the things which was, I think, interesting to talk about was with like one of the scikit-learn maintainers. I mean, scikit-learn, it was built a while ago. It's very NumPy based. If they had mentioned, like having worked a lot on some of these like performance aspects of scikit-learn, if they were to rewrite it now from scratch, and who knows if this is going to happen, or if somebody else is going to do this, like they would probably use something instead like DuckDB or Polders, just because you can get, not because you necessarily need like even the distributed like backend aspect of things, but because you can benefit from the query planning aspect to be a lot more efficient, and that you don't have that with NumPy. So that's like one of the areas which people are looking at. Another thing where there's kind of like a lot of active work is, and I think Anjali mentioned this a little bit, was on the inference side. So with something like IbisML, you're looking to handle both the training and inference aspects. However, like as somebody had asked the question, what about like, cross-validation, hyperparameter tuning workflows, a lot of these things which require this like transfer back and forth between like your modeling, like your technology that you're using for like model training and so on, which is not going to be on your database, versus if you're going to be using things on for like wherever your data resides, where you're doing your earlier feature preprocessing. So where does this feature, last mile feature preprocessing belong? But on the inference side, a lot of models are a lot easier to kind of infer on like database infrastructure, either because you can just wrap it in a UDF and your inference can be either on like a batch UDF or like a single point UDF sort of thing, right? And you just do like a function call. It's not like a training step where there's maybe like a lot more iteration or like having to kind of go across a lot, like the full data set, right? That becomes oftentimes intractable. So there are some, so there's like, I think Posit is one of the sponsors here. They've fairly recently released Orbital, which uses Ibis under the hood for converting scikit-learn pipelines to SQL for inference. Another thing which is interesting is kind of like more broadly using more broadly looking at both the training and inference side, but doing all of this leveraging more like custom UDFs, especially through some engines and Rust extensions like Data Fusion. So there's another company called Zork Labs, which is heavily looking at and using Ibis for this abstraction layer and doing the handoff to specialized engines that are based on UDFs. And I think the last thing, which is kind of worth mentioning, is that this is still like very much an evolving space, and it's hard to tell what's going to win. One of the big areas here is, or one of the big things which kind of think about here is, with this, we talked about like, okay, having to transfer the context between your databases, which are good for like large scale data processing and your be like training infrastructure and so on. And the thing is, like, once it's in something like it's like a Snowflake or something like that, in general, you would say like, well, it's there, now I need to like get it out and get it to my training infrastructure. And that becomes very inefficient. But this is also changing in a way as you see this rise of like data lake houses and things like Iceberg, and the fact that you can use external tables for a lot of these kind of distributed compute backends. Where Snowflake, before Snowflake was very much like this, just as an example, I know I'm talking a lot about certain engines, but basically Snowflake is a kind of very commonly used like database that's used for like analytics and for, and you could, Snowflake is both like your, all the way from your like API layer, and it's got your engine, and it's also that storage, but now you can use it as external tables pointing to like your Parquet files. The biggest aspect is that if you are having your data more laid out in like, Iceberg tables across there, and you can also read that, and if that's accessible to read, but it's also queryable by Snowflake and writable by Snowflake, that can also be read by your model trainers, and you don't have this problem of data transfer, which is where these kind of approaches, again, become more, a lot more feasible, right? Because the biggest problem and the biggest bottleneck of data transfer is gone. So I think that like, yeah, that's kind of just that long story short of what's kind of the state of things, what you should like definitely be looking at using now, if you haven't already, or definitely exploring what are some things to more keep an eye on, and could be interesting to watch developments and see kind of what wins out in this space. And with that, I think that is pretty much all of the content that we have for today. Yeah, thank you so much, everybody, for coming. Also, like, again, if you are curious about and want to learn more about Ibis, its place in the ecosystem, how it fits in with all of this, I'll be here all week. Anju will also be here tomorrow, and also be having a talk kind of more broadly focused on like your modern composable Python first data stack and how Ibis plays a role there, and kind of what are some of the developments more from that data engineering perspective as well. We talked a bit more on the ML perspective, but more on that kind of data engineering side, and how you can use things on Wednesday if anybody's curious. So yeah, thanks again.